Hello and welcome to this revision session for Paper 2 for AQA A-Level Physics, which links into the topic suggested for the Advanced Examination Information for the 2022 examination. So what we're going to be doing in today's revision session is looking at how to answer examination questions on A-Level Physics Paper 2. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how do you prepare for this revision session? So when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this section write out your working out and your answers to the questions in the revision session. When doing this, make sure you write in full sentences to show the full working out, whilst in the right hand side in this section write down any piece of information which you find useful or any hints and tips on answering questions from this revision session, and at the end of the revision session write up these notes into a revision sheet for you to use independently. So what are your tips to revising AQA A-Level Physics? So first step is to learn the key facts. So use revision guides, class workbooks, student prep notes, textbooks to learn the key ideas of the course, and you may wish to make mind maps or write out notes yourself to learn the knowledge. The second step is to use Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to retrieve your understanding from using your own cue cards. And the third step is practice. So practice examination questions by using exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. And you may wish to do this practice by downloading your own examination past papers to do this. So what should you be doing? Learn the key facts, test yourself, practice exam style questions. So let's have a look at the first topic of thermal physics. So it says figure 1 shows the variation of pressure P with volume V for a fixed mass of gas as it's compressed from volume V1 to a volume of V2. There is no transfer of heat energy between the gas and its surroundings during this compression. So estimate the work done on the gas during the compression from V1 to V2. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that when you get a PV graph in your exam, to calculate the work done on the gas or away from the gas, it's going to be the area under the graph. So what you should be doing is working out the energy per small square, which is going to be 0.2 joules, by looking at the scales of P and V and multiplying them together. And then you can work out the total number of squares by counting them or working it through with a shape under the graph, and therefore you get an answer between 35 joules and 38.2 joules. The next question says that the density of the gas is 0.179 kilograms per meters cubed when the volume is V1. Calculate the number of moles of gas present, with a mass of 1 mole of the gas is 4 times 10 to the minus 3 kilograms. So pause the video now, then unpause the video when you want to go through your answer. Well, for this type of question, we've got to remember that the mass of the gas is equal to density times by volume. Now, you know that's because density is mass over volume. Now, you really know this is where we're going in the question because we're given density in the actual blurb of the question, and mass as well. So we can work out what the mass of the gas is by saying density times by volume, and you can read the volume off the graph. So you can read the volume of the gas off the graph at V1, so we can work it through, and we can work out the mass is therefore going to be 2 times 10 to the minus 4 multiplied by 0.179. What we can then do is say that the number of moles is going to be equal to the total mass of the gas divided by the mass of 1 mole. Therefore we get 8.95 times 10 to the minus 3 moles. The next question says, calculate the increase in temperature of the gas as a result of it being compressed from V1 to V2. Then explain in terms of movement of particles why the pressure of the gas increases when it's compressed from V1 to V2. So pause the video now, then unpause the video when you want to go through your answers. Right, so how would you work it through? Well, we're trying to work out temperature and we've been given P and V. So the obvious place to go is say PV is equal to nRT, an equation given to you in your equation book for your exam. You can then work out your temperature by taking any value off the graph really, but I would say either V1 or V2. So you can take either temperature by working it through and taking the values of P and V on the graph. And then we also know the value of the number of moles from the previous question. So what what we can therefore do is therefore work out what the value of T is going to be by working out what the change is going to be 24.2. My apologies. That would be working it out, the increase to equal 328 by working it through from the values worked out from that particular equation. Now the next question is pretty much asking you, why does an increase in temperature cause an increase in pressure? Well, what's going to happen is if we increase the temperature, the internal energy of the gas is going to increase. So this gives our gas particles more kinetic energy. Now the pressure will increase because you've got a greater change of momentum of the gas atoms when they collide with the walls of the cylinder. It's always important to link the pressure to the rate of change of momentum of the gas particles as they collide with the container that they're in. Now, why would you have a greater change in momentum of an increased temperature, which leads to an increased kinetic energy of the gas particles? Well, there'll be firstly a greater frequency of collisions of the gas particles with the side of the cylinder, and also the gas particles themselves will have a greater momentum because they've got a higher velocity, so therefore the change in momentum for each collision is also going to be greater. Let's now have a look at some questions on radioactivity. So the first question says, a stationary uranium-235 nucleus decays to a thorium-231 nucleus by emitting an alpha particle. 98% of the total energy released in the decay is transferred to the emitted alpha particle as kinetic energy. Explain in terms of mass of the nuclei why the total binding energy of the nuclei must increase as a result of this decay. So what you should do is pause the video now and then unpause the video when you want to go through your answer. Right, so how would you answer this type of question? Well, it's important to note that in any nuclear decay, the mass of the product nuclei is going to be less than the mass of the original, the mass of the uranium nucleus. Now, we call the increase in the mass here is the mass defect. So the idea of your binding energy then links by doing E equals a delta mc squared, where m is the mass defect. Okay, so therefore you can say that the binding energy is the energy equivalent of the mass defect or the mass deficit. Now, the next question says, a stationary uranium-235 nucleus decays to a thorium-231 nucleus by emitting this alpha particle. So table 2 shows the binding energy per nucleon of the nuclei involved in the decay. Calculate the speed of the alpha particle just after it is emitted, where you're given the mass of the alpha particle in the question. So pause the video now, then unpause the video when you want to go through your answer. Well, how do you answer this particular question? Well, it's important that you can work out the energy released in this particular process. So what we know is we start off with uranium, and we're producing thorium, and we're producing helium in this particular question because we're producing the alpha particle, which is helium. So what we would say is the energy released is equal to the binding energy of the thorium plus the binding energy of the helium minus the binding energy of the uranium. Now, it's important to note that when you're doing this, the table gives you the binding energy per nucleon. So you've got to multiply all those values in the table by the nucleon number of the particular element. So for 235 for uranium, 231 for thorium, and 4 for helium. What you would then do is you would then work out your energy released in joules to be 0.59 times 10 to the minus 12 joules, because remember the values of picojoules that they'll give you. You can then multiply that value by 0.98. Why 0.98? Well, because 98% of the total energy is then transferred to the kinetic energy of the alpha particle, which is what we're trying to work out. So therefore, once we've worked out our energy value, we can then say E equals a half mv squared, the kinetic energy equation. We know the mass of the alpha particle because it's given in the question. We've just worked out the energy of the alpha particle from our sum just previous, so we can work out V to be 1.3 times 10 to the 7 meters per second. The next question says, a plasma containing nuclei of 2 isotopes of hydrogen, 2H and 3H, is considered to be a possible fuel for fusion reactors in the future. The plasma must be heated to a high temperature to provide the nuclei with the minimum kinetic energy to enable the fusion reaction to occur. Explain why the nuclei in the plasma require a minimum kinetic energy for this fusion reaction to occur. So pause the video now, then unpause the video when you want to go through your answer. Well, this question is pretty much asking you to explain the nuclear fusion process. So the idea is that you've got two positively charged nuclei. So the two nuclei are going to want to repel each other. So when you need a high kinetic energy, because that will transfer to electrostatic energy due to the repulsive nature of the two positively charged nuclei. Now we need to have a high enough kinetic energy so they can get close enough so that kinetic energy will transfer into electrical potential energy, so that the nuclei are close enough so that the strong force can bind the two nuclei together. Remember, the strong interaction is the binding force in our fusion process, and the two nuclei need to be close enough for the strong interaction to be within the range for it to take hold. The next question says, the radius of a 2H nucleus is 1.51 times 10 to the minus 15 meters. So show that the distance between the 2H nucleus and the center of the 3H nucleus is about 3.2 times 10 to the minus 15 meters when they're just in contact. So pause the video now, then unpause the video when you want to go through your answer. Well, it's important to note that in these types of questions we need to look at the idea of how do you work out nuclear radius. So we know our nuclear radius R is equal to R0 a to the power of a third. Now we know R0 is 1.12 times 10 to the minus 15. So what we can therefore do is we can therefore use R equals R0 times by a to the power of a third for the radius of helium by hydrogen, 3 hydrogen. So we would just go, it would be 1.12 times 10 to the minus 15 times by 3 to the power of a third. So you work it out to be 1.73 times 10 to the minus 15. You've already got the radius of the 2H nucleus, which is 1.51 times 10 to the minus 15. So you add the two values together and you get an answer of approximately 3.24 times 10 to the minus 15 meters. The next question says, assume that the 2H and the 3H nuclei fuse when they are just in contact. Calculate the minimum total kinetic energy that would allow a 2H nucleus and a 3H nucleus to fuse. So pause the video now, then unpause the video when you want to go through your answer. Well, it's important to note in this situation our kinetic energy is being turned into repulsive electrical potential energy due to the positive charges of both the nuclei. So we can equate the two. So we can say that kinetic energy is equal to Q1 Q2 over 4 pi epsilon 0 R, the equation for electrical potential energy. So we can then substitute our values in. So we've got the charge of one, because remember it's going to have one proton. The charge of the other one, again, one proton. We know the separation R because we've just worked it out in the previous question, and we know 4 pi epsilon 0. So therefore we can work out what the kinetic energy is going to be, and therefore we know 7.1 times 10 to the minus 14 joules. The next question says the equation for this fusion reaction is shown here. The table 1 shows the mass of each particle involved. Calculate in joules the energy released when this fusion reaction takes place. So pause the video now, then unpause the video when you want to go through your answer. So in this type of question, it's important to work out the difference in mass in this particular process. So what you do is you do the mass of the helium and the mass of the neutron minus the mass of the deuterium and the mass of the tritium, 2H and 3H. What we can then do is find our mass difference, and that's our value in U. Now we can convert from U into an energy unit, MeV, by multiplying that value by 931.5. That gives our answer in MeV. Then we can convert it into joules by dividing by 1.6 times 10 to the minus 13, because that's our conversion factor from MeV into joules. So we get our answer to be 2.7 times 10 to the minus 12 joules. The other way you could have done it is worked out your mass in U by the same process, then multiply by 1.661 times 10 to the minus 27 to get your answer in kilograms. Once again, that conversion factor is given to you in your equation book. We can then work out our energy release with our mass in kilograms by doing E equals mc squared. The next question says an alpha particle with an initial kinetic energy of 8 MeV approaches the center of a nucleus of gold 197. Calculate the distance of closest approach between the alpha particle and the nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this question? Well, again, it's the idea of two positively charged objects coming close to each other. So we can say our kinetic energy is equal to our electrical potential energy. So we say EK is equal to Q1, Q2 over 4 pi epsilon 0 R. Now we want to work out R, so we make R the subject. But what's kinetic energy going to be? It's going to be 8 times by 1.6 times 10 to the minus 13, because we're converting it into joules. We know the charge of the alpha particle to be 2 times by 1.6 times 10 to the minus 19, because it's an alpha particle, so it's got 2 protons. We know that it's got 79 protons in gold from the information given in the question, so it's 79 times by 1.6 times 10 to the minus 19. You can work it all through to be 2.84 times 10 to the minus 14 meters. The next question says, discuss why electron diffraction gives a more accurate value of a nuclear radius than the using the distance of closest approach of alpha particles. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to explain the difference between electron diffraction and the distance of closest approach. Now, the important thing to note is that the most important idea is that the distance of closest approach depends on the alpha particle energy, because it's turning kinetic energy into electrical potential energy. So your value for your separation, R, which you just calculated in the previous question, is dependent on the actual kinetic energy of the alpha particle. Now, the distance of closest approach is dependent on the fact that the alpha particle does not collide with the nucleus. Rather, it gets close enough to then be repelled by the positive interaction. So the closest approach is not the nuclear radius, it's actually the nuclear radius plus another distance, okay, because the alpha particle will not touch the nucleus itself. Now, for our electron diffraction, it's a more accurate value because the de Broglie wavelength of high energy electrons is of the order of the nuclear radius, so it will have diffraction because the biggest diffraction occurs when the de Broglie wavelength is equal to the size of the gap it's going through, which is in this case the nuclear radius, so you'll get large diffraction angles, so it's very easy to measure. Now, you'll also note as well that because alpha particles have the same mass on order of magnitude as the nucleus itself, you'll actually get our values affected by a momentum transfer or a nuclear recoil because of how similar in size they are. The next question says, describe with reference to their energy the role of neutrons in a thermal nuclear reactor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So in this case, neutrons are released in fission. So the fission process will release some neutrons to be free. So these fission neutrons, if you want them to then fission further nuclei, have to be slowed down. So they've got to have their kinetic energy reduced. So this is achieved, this slowing down, so it has a smaller kinetic energy value, is achieved by collisions with the moderator atoms, so therefore that these neutrons are moving slow enough to be absorbed by uranium nuclei to sustain the chain reaction. The next question says, describe the function of control rods in a thermal nuclear reactor, and your answer should include one example of a suitable material for a control rod and its properties. So pause the video now, then unpause the video when you want to go through your answer. Right, so a suitable material for a control rod would either be boron or silver or cadmium, indium, hafnium. They're all examples. I mean, the most common example is boron. Now, what happens in a control rod is a control rod will control, as the name suggests, the rate of fission in your reactor. So what the control rod can do is it can maintain the rate of fission that you want in your reactor. So the control rod does this by absorbing neutrons, because if it absorbs neutrons, it prevents these neutrons from being absorbed by other uranium nuclei and causing further fission. So you've got to know that if you raise your control rods, less neutrons are absorbed, so the fission rate will go up because more neutrons will encounter the uranium nuclei. But if you lower your control rods into your reactor, well, then more neutrons are going to be absorbed, so less neutrons will be absorbed by uranium nuclei, so there'll be less fission. If you wanted to shut down your fission reaction as soon as possible, you will completely lower your control rods down. Let's now have a look at some questions on magnetic fields. So this question says a rectangular coil shown in figure 2 rotates at a constant frequency of 40 Hz about an axis that is perpendicular to a uniform magnetic field of flux density 0.15 Teslas. The coil has a length of 6 centimeters and a width of 4 centimeters and has 25 turns. Calculate the peak in EMF induced in the coil. Calculate the root mean square value of the EMF induced in the coil. So pause the video now, then unpause the video when you want to go through your answers. Right, it's important that if you look in your equation book for AQA A-level physics, you'll notice there's an equation for peak EMF is equal to BAN omega. Now we know omega from our circular motion topic is 2 pi f. Now you've been given F, you know B, you know A by calculation. Now again, remember they're given you in centimeters and you work it out in meters. And we've got our value of N, we know how many turns there are, okay, because it tells you it's 25. So you put all these numbers in and you work it out to be 2.26 volts. The next question says calculate the root mean square value of the EMF induced in the coil. So what you can then do is you can therefore say the root mean square EMF is going to be the value divided by square root 2. So you do 2.26 divided by square root 2, which is 1.60 volts. The next question says, for the same idea, a 6.8 ohm resistor is connected across the output of the coil. Assume the coil has zero resistance. Calculate the mean power dissipated in the resistor. Then to increase the mean power dissipated in the resistor, it suggests that either the magnetic flux density or the angular speed of the coil could be doubled. Deduce the effect of each of these possible changes on the output of the coil. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out power dissipated? Now in the previous question you just worked out EMF, which in this case is V. So we can say that power is equal to V squared over R. So you've just in the previous question worked out what V is. You've been given R, which is 6.8. So you do V squared over R and you get your answer out to be 0.38 watts. Now this next question is saying to us that the angular speed of the coil could be doubled or the magnetic flux density could be doubled to increase your power dissipated. Now you've got to indicate firstly that if you double your magnetic flux linkage, so your magnetic flux density, because we know that EMF is equal to BAN omega. We know that if we double B, we'll be doubling V, we'll double in EMF, and we also know that if we double the angular velocity omega, we'd also be doubling EMF, because remember we said BAN omega is equal to EMF. So therefore, if you double both of them, as the idea is that each one has a doubling effect, so the overall effect on EMF is going to be to the power of 4. But also note that if you double omega, it's spinning faster, so not only will it double the EMF produced, it'll also double the frequency of your alternating voltage produced. The next question says, figure 4 shows the arrangement that a student uses to investigate electromagnetic induction. The voltmeter connected across coil Y can be measured both positive and negative potential differences. The student opens the switch and the current in coil X decreases to 0 in a very short time. Describe what happens to the reading on the voltmeter during this time. Go to explain why this happens. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's the idea of our value, we're producing an EMF. So what's going on here? So we're getting a large EMF at first and then it's going to drop to 0. Why is that? Well, because we know EMF produced is related to the rate of change of flux linkage. So what would happen is if you open the switch and you reduce the coil so you reduce the current in coil X to 0, well, you're going to reduce the magnetic flux linkage, because when a current flows through the coil X, it will become an electromagnet and therefore have a magnetic flux field. So therefore what will happen is if the current is turned off, as it's an electromagnet, it is no longer a magnet, so the magnetic flux linkage will decrease to 0. So what will happen is, because there's a change in magnetic flux linkage via Faraday's law, that indicates to us we will induce an EMF, but ultimately that change disappears because it's going to stay at a value of 0. So because there's no change, therefore there's no EMF induced, so it will drop to 0. Now it's also important to note that with Lenz's law, it's going to be the opposite sign to the first reading, because what's happening is that the EMF is produced in the opposite direction to the change that caused it, so it's going to be a negative value. The next question says the arrangement shown in figure 4 can be used as a transformer when coil X is connected to an alternating current supply. Explain the reason for using a laminated core. So pause the video now, then unpause the video when you want to go through your answer. It's very important you can explain why we use laminated cores in transformers. Now, laminations will reduce energy loss, so will increase the efficiency of a transformer. So it's important to note that this occurs because the laminations will reduce the size of eddy currents in the iron core. So that's a really important idea, because a lot of the inefficiency in a transformer is caused by eddy currents, currents of the magnetic field going in the opposite direction to the intended one. Okay, so the laminations will reduce that. Now remember, lamination just means to insulate with plastic. The next question: a student does an experiment to investigate electromagnetic induction. She drops a magnet vertically through a coil of wire. The coil is connected to a voltage sensor and a data logger shown in figure 9. Explain why an EMF is induced as a magnet falls towards the coil. So pause the video now, then unpause the video when you want to go through your answer. Well, once again, how can we say there's an EMF induced? Well, EMF is induced when there's a change in magnetic flux linkage. That is Faraday's law. So as the magnet will fall through the coil, there will be an increase in the magnetic flux linkage, because now the magnet is inside the coil of the wire itself. The next question says, explain why V1 and V2 have opposite signs, because figure 10 shows a variation of the induced voltage V with time t after the magnet is released. The durations T1 and T2 and maximum values V1 and V2 of the two peaks are labelled. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, it's the idea that with Lenz's law, EMF is induced in a direction to oppose the change in flux linkage that produced the EMF. So what will happen is, as the magnet is going into it, it's going to produce a EMF in the opposite direction, a negative. However, then when it goes out of the coil, it's going to be producing a positive EMF, because now the magnetic flux linkage is decreasing. So we'll say that when it's increasing, when it enters, it's going to produce a negative EMF, and then as it leaves, it's going to produce a decrease in magnetic flux linkage is producing it, so therefore it's going to be a positive value. Remember, again, it's opposite values because of Lenz's law. Now the next question says, explain why the magnitude of V1 is less than the magnitude of V2, and explain why T1 is greater than T2. So pause the video now, then unpause the video when you want to go through your answer. Right, again, it's important. Why is V1 less than V2? Well, the magnet is going to go slower when it's entering because it's being dropped. So as it's falling, it's going to be accelerating due to gravity. So therefore, when it's going in, there's a smaller rate of change of flux linkage. So with Faraday's law, the rate of change of flux linkage is directly proportional to the EMF induced. Because it's going slower, there's a smaller rate of change. Therefore, a smaller EMF is going to be induced. Now, why is T1 greater than T2? Well, again, same reason. The magnet is accelerating downwards, so the time from the top of the coil to the center of the coil is going to be greater than the time from the center to the bottom of the coil, because it's going to be moving faster the more it's falling down due to the acceleration due to gravity. Now again, remember, EMF is going to be zero in the magnet at the center of the coil, because at that instantaneous moment there's going to be no change in flux linkage at that particular point. Now let's have a look at some questions on gravitational fields. So the first question says, a space mission is planned to remove a small boulder of mass 8.2 times 10 to the 3 kilograms from the surface of an asteroid. The gravitational field strength is 1.77 times 10 to the minus 4 newtons per kilogram at the surface of the asteroid. Calculate the weight of the boulder at the surface of the asteroid. Then explain why gravitational potential is always a negative quantity. And then the gravitational potential at the surface of the asteroid due to the asteroid's gravitational field is minus 3.99 times 10 to the minus 2 joules per kilogram. A spacecraft of mass 1.8 times 10 to the 4 kilograms removes the boulder to position when the gravitational potential is negligible. Calculate the work done against the asteroid's gravitational field. So pause the video now, then unpause the video when you want to go through your answer. Well, the first question is saying that weight is equal to mass times by gravitational field strength. So times your mass by your gravitational field strength and you get 1.45 newtons. Now, why is gravitational potential always a negative negative quantity? Well, like we've mentioned before, we define potential to be zero at infinity because it's now outside of the gravitational field at infinity, so therefore there's no influence from the gravitational field on that object. So its gravitational potential and its gravitational potential energy is going to be zero. So therefore, because we've got to put work into the object to get to zero, because we've got to put energy in to get the object out the field, because gravity is always an attractive force, if we've got to put energy in to get to zero, the potential must be a negative value. Now the last question is, how do we work out the work done? Well, we know that the work done is going to be the mass of the object times by the change in gravitational potential. So what we can do is we can therefore say it's going to be 1.8 times 10 to the 4 multiplied by 3.99 times 10 to the minus 2. So therefore you can work it out to be 1050 joules. Now how do we know that the change in gravitational potential is 3.99 times 10 to the minus 2? Because we know that at infinity the value of potential is zero, so the change is going to be from the value in the field to zero. The next question says the boulder will be placed in a circular orbit around the moon. Show that the period t of the circular orbit of the boulder around the moon is given by the equation t equals the square root of 4 pi squared r cubed over gm. Then the orbital period of the orbit around the moon is 24 hours. The mass of the moon is 7.35 times 10 to the 22 kilograms. Calculate the radius of the orbit. So pause the video now, then unpause the video when you want to go through your answer. Well, it's important that when you're trying to derive the time period of a circular object, always remember a couple of things. Firstly, we can equate our centripetal force to that of the gravitational force, because the only thing that's causing a circular orbit is going to be the gravitational attraction between the moon and the boulder. Now, it is still a circular motion, so we can say it's the centripetal force. So we say the centripetal force is equal to the gravitational force. So we could use either mv squared over r or m omega squared r as our centripetal force. I think we'll use m equals omega squared r, and that equals g big M small m over r squared. The two smaller m's will cancel through, and then we can rearrange to therefore make t the subject. We might think, where has t come from? Well, we've got omega in our equation, and we know that omega is equal to 2 pi over t. That's an equation you've got to remember. Angular velocity is the change in angle, which is going to be 2 pi radians, over the time of one orbit, and then we can rearrange and make t the subject. Now for the second question, what we've then got to do is use that previous equation. We've got to then say, well, we know what 4 pi squared is because it's just a constant. We know r cubed from the question. We know how far away it is. We know what the mass is because the mass of the moon is given in the question, and we know what g is. It's just a gravitational constant, so it's 9.75 times 10 to the 6. The next question says, one of the moons of Jupiter is named Io. The mass of Io is 8.93 times 10 to the 22 kilograms. The gravitational potential due to Io at its surface is minus 3.27 times 10 to the 6 joules per kilogram. State what's meant by a gravitational potential of minus 3.27 times 10 to the 6 joules per kilogram at the surface of Io, and show that the radius of Io is approximately 1.8 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. So firstly, what's the definition of gravitational potential? Well, gravitational potential is the work done per kilogram. And then the second thing is that it's done from bringing a mass from infinity to the surface of Io, to the surface of the object. So therefore we will say it takes 3.27 times 10 to the 6 joules to move every kilogram from infinity to the surface. Now remember, we always say it's from infinity to the surface of the object. Now then, how can you work out the radius of Io? Well, we know that gravitational potential is in this equation is V is equal to minus gm over r. Remember, it's always a minus value because gravitational potential is always a negative. We know what gravitational potential is. We know what the mass of Io is from the question, so therefore we can work out what r is because g is just a constant. Again, why do we use this equation? Because we've been given gravitational potential in the question. The next one says one of the moons of Jupiter is named Io. The mass of Io, as we talked about before, is given to be 8.93 times 10 to the 22 kilograms. A volcanic rock of mass 3 kilograms is ejected vertically upwards from the surface of Io with an initial velocity of 760 meters per second. The rock reaches a maximum height h above the surface of Io. Show that the rock's gravitational potential energy at height h is approximately minus 9 megajoules and calculate the value of h. So pause the video now, then unpause pause the video and you want to go through your answer. Right, so how do you answer this particular question? So what we'd say is we're trying to work out the gravitational potential energy. Now we can say that it's going to be equal to a half mv squared, because what we'll say is that that kinetic energy is going to turn into gravitational potential energy. So we can say potential energy is equal to a half mv squared, and therefore what we can do is we can therefore link this in together. We can add our initial gravitational potential energy, because we know that it's obviously we've got the radius of Io from the previous question, so we can say that mgh from that part, and then you can add it onto the kinetic, and therefore you can work it out to therefore say 8.9 times 10 to the 6. Now then, how do you calculate h? Now it's very important here, because we've now projected it off the surface and the gravitational field strength has changed significantly. We can't use an equation from GCSE where we say potential energy is equal to mgh. What we've got to use now is we've got to use our more sophisticated equation, which is that gravitational potential energy is equal to G big M small m over r. We can then rearrange this and make r the subject. We know what E is from our previous question. We've got big M, the mass of Io. We've got small m, the mass of the rock. We've got G because it's a constant, so we can work out r, which is our height going to be. But obviously again, remember to subtract the radius of the moon from this, because we're calculating h. Okay, so we'll subtract our radius of Io because we're working out the difference from the surface as opposed to the center of the system. So we get 1.8 times 10 to the 5 meters. The next question says another rock of greater mass is ejected vertically upwards from the surface with the same initial velocity. State and explain how the height reached by the rock of greater mass compares to h. So pause the video now, then unpause the video and you'll want to go through your answer. So what do we know? Well, the idea is the height will be the same, because as we should be aware, we're saying that the kinetic energy is going to be turning into the potential energy as it's being ejected vertically upwards. So if we said a half mv squared is equal to G big M small m over r, the two masses, the mass of the projectile is going to cancel through on both sides. So therefore it indicates to us that actually the mass of the object does not affect how high something will go up, and that's a very important idea in gravitational fields. The escape velocity of a gravitational field does not depend on the mass of the projectile, only the mass of the actual object producing the gravitational field. And because both of them are being ejected from Io, therefore the mass of the projectile does not make a difference. So that brings an end to our revision session today. I hope you've been successful and you've learned in today's revision session. If you have been, you should be able to answer A-level physics examination style questions. You can assess your understanding on A-level physics and understand what topics you need to improve upon for A-level physics. So thank you very much for watching this revision session on the paper 2 topics for AQA A-level physics based on the topics coming up on the 2022 physics examination. Thank you very much for watching and have a lovely day.